Stefan is going to talk about parallel Rust, parallel programming in Rust. Thank you.
Thank you very much. So, I will be walking over there and back. I'm trying to record this, mostly because I want to know if I have any bad habits. Plus, if the recording actually works, then your laughter might be on it. And I hope that the sound is terrible. Yeah. This is LaTeX, by the way. Old stuff never dies. So, let's go through our index or table of contents. Yeah, it has this loading bar here. So over time there will be some orange growing. Yeah, timetable, we had that already. Important part is this. If you use Rust, parallelize a lot, and sometimes it's already done for you. Just a little bit about me. Oh no, I forgot to update the Paris line. Okay, so this line is wrong. This is Rustfest. It's where the t-shirts from. Rustfest is the European conference for Rust. This line describes Paris, which was in spring. Rome was in fall, and the next one will be also in fall, because we have to take 2 steps back and look at our project and say, okay, we are doing the same things wrong every time. We actually need to fix them. So that's what we're currently doing, and by any chance there will be a Rustfest in Barcelona, in Spain, probably in September, more or less. Yeah, we organized some talks. This is an alternative festival. I tried to translate this. I'm not sure if it's correct, if it makes any sense.
It does.
Hooray! So if you want to go to a very alternative festival in Switzerland, check this out. It's in July. Okay, side projects. Some people might know me from there. It's the Rust ThreadPool.
I think I will use that actually.
Hooray! I think it's the second most widely used ThreadPool currently. So it's also the oldest one, so it doesn't have futures or anything. It has. We started to redesign the API like over a year ago, but yeah, we don't want to break too much stuff. So we see how that goes. I also did some cluster work. So SGE, Son of Grid, is a Linux cluster manager. Originally developed as Sun for Solaris. By the way, use your own infrastructure when you can. The internet is decentralized and it only stays that way if we use it. But today I was in a small coffee house and they had IPv6 only Wi-Fi. It was 40 megabits fast, which was great, but you can't do Rust without IPv4. Because you can't do GitHub without IPv4. And the Rust build system needs that. Also, you can't complain about it because Twitter is not with IPv6. So naturally, the next step, you go to the forum of your Rust language and hooray, it works! Now I can complain. Log in. Oh, authenticate with GitHub. Yeah. So I thought I was being smart. So let's use a VPN, of course. Ports are blocked. Yes. Okay, let's use the VPN I set up on port 443, the HTTPS port. Yeah, that one is v4 only, so I had to read the book. So bad. Okay, what will we learn today? Loops. I'm guessing here that everybody in this room is programming, more or less. Should we do the hand waving thing? So, programming? Yeah, so let's start with hands up. Is everybody here? So your hand should go up. Now lower your hand if you don't know what a loop is. Okay. Lower your hand if you don't program. Still nice. Okay. Lower your hand if you don't know what a function is. Still good. Okay. Iterators. Okay. Parallel programming. Woo. Okay. Okay. Atomics. Still, you all know what atomics are? Okay. You know what the memory fence is? You know that there are memory fences for memory fetches. Okay. You also know that there are reordering barriers for CPU instructions, as well as memory instructions. Nice, okay. We won't use half of that stuff. Alright, let's start with loops. So, who can guess the language of this program? C, yes. Notice there is go-to in C. But still C, yes. This is valid in C04, I think. The latest C, anyway. It has a bunch of problems. And I use these names here from a book. And I'm not sure if it's common around here. It's a very funny book in German from Marc-Uwe Kling. It's about digital age. It's called Quality Land, which is Germany after they renamed themselves after some political scandal. Okay, so C also improved a bit over time. There is this for int. This came with C98, I think. Plus, you could get a speed up by having pre-increment operation instead of post-increment operation. Today's compiler usually optimizes this away, but still. Here's our protagonist list. These are the main protagonists. They translate into Peter, unemployed, Sandra, system administrator, and Peter Cook. Because in that book, the last name is always the job the parent of the same sex had when they created the child. So 9 months before birth. It's really bad. Okay. So, how do we do that in Rust? Well, we can't go back to goto, there is none. Also, the length is in the type already if you have constant data, so you don't have this length trick. And yeah, I will be using this. I copied in this flag here so that you see. You probably shouldn't use it, but if you ever get into the case where you generate code and it gives you this ugly warning, then you can allow ugly code. There used to be a great lint which was allow bad code, but then some people were offended by it. But no, I mean, when I tag something as bad code, it's bad code, so it has to stand out. Okay, so how do we iterate over that? Well, easy peasy, the C start, right? There's a problem with this, actually two. So one of the problems is here. This semicolon is optional, and currently the return value, this expression returns something. The index increased, and it gets lost for now. But in the future, there's a good chance that this block will return the last of these values. So that might come in as a problem at some point. Plus, this index access might give a panic if we do out of bounds index. So it's a problem. Good news is the compiler will probably inline the whole thing because it's so short and it knows most of the stuff at the compile time. So we can make that safe by using the for each. For in is already the reference to reference here. We're done. If we forget to add ampersand and have multiple for loops over the same thing, you get something like data was already moved, or access after move, access, just remember that. Okay, we can also use the iterator explicitly. So we create an iterator object here, and then we consume it with the construct. Or we can also rewrite it in functional and just say for each. If you have to be backwards compatible with old Rust, like 1.14 or something like that, then for each isn't there. For each is, I think, 1.22 or something like that. There are like two breaking points you actually have to remember. So one is 1.13 is the question mark operator, and 1.20-ish, 22-ish or something like that is for each. Because before that you have to use fold, which does the same. Okay. Oh, and if you have questions, just like wave or shout. So, what's an iterator? In Rust, it's a trait, and that's all the stuff we need to know. That's the absolute minimum information the iterator needs to fulfill. Has to have an item. This type here makes it generic, although it doesn't have the turbofish syntax. And then the next with option, and option is our null pointer replacer. So, ooh, it's getting faster. All right. So, we take the example from before. So why would you do that? Why would you complicate the syntax? Well, I usually say filter maps and all the technical stuff, but one other thing is maintainability. If you have short functions that do one thing in one line, can help. It depends a bit on the people. If you have beginners in the whole project, it doesn't help. It really doesn't help. But if you have people that come from Haskell, like I did, you look at it and like, oh, nice! I can enable and disable filters with like 2 backslashes. Or forward slashes. So, hooray, we're done. It's also nice for the compiler because it can optimize. You have this functional style, the compiler knows you only touch one element at a time, and then it can do some hardware optimization and process 4 elements at a time. Plus, there's also a great talk from Pascal Hertleif. He gave it in Rome, and he had also the declarative, we go over here. Declarative programming is more or less functional programming with Rust. So when he did his slides, he showed us some Monday morning code, and then asked the viewers, hey, what's wrong with this code? And they found so many errors. Some of them he didn't plan. So plus, you get the speed up if you use these kinds of functions, because especially if you use take or skip, then the compiler can insert early returns, so you don't loop over the whole data structure. Links are here. I will upload the slides afterwards. All right, let's go on. Another thing most of us do is we have these little tiny languages that we write to parse, I don't know, unstructured data or config files or old code. Something that's really handy is split, because split is an iterator. And we can collect split into a vector if we'd like, then we know how long it is. But we risk, whoops, wrong button. We risk out of bounds panics, so we don't want that. So what I've seen people do is they collect into the vector to know how long it is, and then take another iterator to loop over it again. Because when iterators are empty, they return none, and then you can so much easier. It's so much easier to check to return. Okay, so what are we going to do? Here we assume that every person has just the first name and the surname, and that they are separated by a space. So we go through our data, the data from before, and split it. And here we say, okay, split up into the thing that comes first and the thing that comes second. So we create a tuple here, Everybody know what a tuple is? I should have to ask. Tuples? Great, perfect. Okay, we deconstructed already over here. And then we have to see, is it there? If either one of them is not there, then we say, hey, that didn't work. So we have an early return here, exit the function. And if we don't, then we say, okay, let's push them in. And then we have a push. I think I lost the slide there. Okay, and last but not least, here we unwrap it because now we know that they are there. So unwrap and into because, fun fact, we didn't handle strings here. We have a string here in the name symbol, but the split gives us str, so they are views. So here we create an object. These are smart pointers. And here we have to copy them again because we want to have a live string. Because after this line, the name gets given away to something else. And in the end, we say collect. And in the collect, we have some little magic. And the magic is great. Collect has a great magic. And I tried to find the source code of it, but I haven't found it. So what you can do with collect is when you have a sequence of results or options, you can extract that outside of your sequence. And this works with vectors and with lists, and with, vector is a list, maps and hash sets. So with this line we can say, okay, process until there is an error. If there is an error, give me the error. If it's, so this gives us either a correct list or the first error. All right, so this is ugly code, right? So let's improve it a little bit. So first, we use match. So we can get rid of the unwraps, right? We can match on this tuple, create a person if it worked, or we can create the error for everything else. So this underscore over here is the default case for match. If we don't do that, we have to write all the possible cases, so it may take a while. Oh yeah, here's the comment. Magic happened. Case I forgot. Okay, here's the output. And this pretty print comes from this hashtag here. So if you put this hashtag between the colon and question mark, it will inline everything nicely. This is also very good. When you create your own data structure and you implement the debug trait yourself, don't write bytes to the thing that it gives you. Take it as an iterator and say, hey, constructing my name, constructing a block, and then it will indent one more, and then here is a field with that thingy. And then depending on how the format is specified, it will either take multiple lines or one line, or can prepend it with zeros or spaces or tabs or whatever you want to have. Same with the display. All right. So much for the basics. I hope you weren't bored. If so, wake up. Okay, what are we going to do? It's usually one of these things. Thumbnails is a very common thing for parallel stuff because you have to generate lots of them, or maybe on the fly, messages, audio, all that stuff that's real time. Because all the stuff that's slow is usually solved good enough with other languages and nobody cares. So, do we have to use multiple processes? Maybe not. If we program some embedded board that's maybe looking over humans that touch maybe 4 or 10 buttons on some remote, humans are so slow. Imagine your CPU has like 80 megahertz or something like that, or 100. Still so much faster than you would. Press down, hold it, let it go. And be like, oh, this thing is very slow, but I don't care. If you go into hardware, there's interrupts. If you go there, there is a really cool operating system, the TOC OS. It's Rust based. It only works on certain ARM microcontrollers, but then you don't need locks anymore. So you can have locks with the interrupt table. So you manipulate the interrupt table with the type system and then get locks out of that. Very cool. SIMD is the thing that I hinted before. So there are some languages that already do that, like C++. If you use for each or any other algorithms loop thingy, it will create two nested loops. One for start from 0 to the end, and inside that start from here to 4 more, and then loop 4 inside, and then jump outside again. And what this tells the compiler is, hey, why don't you try to process 4 elements at once? And do that with SIMD. And Rust is integrating SIMD currently. I'm not sure if it's already stable, but it might be. Is it? Does anyone know? Could be. There's a crate for that, for sure. Okay, next thing. We actually have stuff that's not the same all the time, that we have to wait for and stuff like that. Maybe some of you have done CUDA. The most expensive part is if you have a branch that one arm of the branch is like way longer. Sorry, if statement has one long part and one short part, that's very expensive for the graphics card. On the CPU we don't have this problem because we have SMP, simultaneous multi-threading, where you can have stuff run independently. But now we have to synchronize stuff. The old approach is a pool, where you have a list of jobs or a fixed size of workers, and then you route in requests and route out requests. Like the Apache web server is probably one of the oldest that uses that. There are other programs that you might use is OpenSSH. OpenSSH doesn't use threading. That's a fork program. So when you create an OpenSSH connection, your connection gets forked away from the server, and that's why you can restart the OpenSSH server without losing the connection, because your process is independent. Very cool. Okay, let's implement something. Do you remember the old pick 3 for Rust? The safety, speed, concurrency? So they get enabled by these two marker traits. What the compiler assumes when you create your own data structure is that they're there, and then it looks for conflicts. So whenever you create data structures with, let's say, just U sizes in it, is it send? Yes, because all the U sizes are sent. Is it sync? No, U sizes are not sync. You create a data structure? Yes.
Perhaps refresh my memory in
Yes.
what is send and what is sync? Is it time ago or is it time ago?
Okay, so send means you can transfer it across boundaries of threads without having problems. You can't do that with, for instance, some file descriptors. There are some file descriptors that are thread local, or sockets sometimes. So, and sync means you can access them from multiple threads at the same time. This does not solve the problem that one thread might start deallocating it while the other one is still using it. But at least when the thing is around, you can call methods on it, write or read to members of the data structure. If we don't have sync and we share something, it must be read-only, or const, or static. If we have static, then it becomes unsafe. I actually tried to measure the difference between those, and it became really, really hard to have the correct value. If we have time, I have another presentation that we can look at afterwards. Does this answer the question more or less?
Yes, thank you.
Okay. So, in the standard library we have SED thread spawn, and then we have to join that again. So when we spawn a thread, we get a join handler. If we just have one task that we want to get rid of and do something else in the meantime, that's sometimes good enough. We can also use pools, where we have fixed size of workers. This is a huge advantage when we have something asynchronous happening, like an event loop, and then sometimes we have work that's offloaded to the workers that we don't overload on our machine. So if the work is CPU bound, you really want to have a worker pool, because when you just add 500 jobs to a CPU and your CPU is only like 128 cores big, stuff gets sluggish. There are two widely used pools, ThreadPool and Futures ThreadPool. ThreadPool is the old one, and the Futures ThreadPool is the new one inside Tokyo. Sometimes the Futures ThreadPool outperforms, plus it can do runtime optimizations, but the ThreadPool can't do by design. Then there is the implicit rayon work stealing. Rayon is an iterator approach where you spawn work with either divide and conquer, like recursion. Then you can have a recursion function that calls itself twice, so you can have one task for your own thread and one task for the others to take. Or we have some indexable access to data parallelism, where I can say, okay, my whole thing is 1 million entries long, I can split it up into 15 chunks and give it away to my workers. Maybe 4 of them work at the same time, but it's still faster than doing other stuff. If you're into academics and simulation, there is timely data flow. Frank McSherry, I forgot his name. Frank did this project while he was in the States. Now he's in Switzerland and continues to improve it. It's a round-based tuple simulator. It's really fast, and he outperforms some smaller clusters with a laptop. So that's really cool. Okay, solved the problem of handling work over and over again, but now we have still to synchronize and communicate. Plus, over-communicating is also a performance killer. So, how do we synchronize that? Here's a small example. Sorry for this compressedness. Oh, this is actually working now. So with Rust 2018, you don't need the extern crate anymore, so this actually compiles. Hooray! So we use ThreadPool from the crate, and with this statement we tell the compiler to link it. And we use channel from the standard library, which is always used. And we say, okay, 4 workers, 8 jobs, we can increment this number if you like. Create this pool the old way. There's a new way, the builder way, where you can select stuff like stack size of the workers, or say, hey, just make auto-detect. I don't want to care how many you create. Then we create a channel. Channel it's in this acronym, it's multi-producer, single consumer. So it's more or less an atomic dick, if you know from other language. Okay. For underscore, again, we ignore the index. We create a range. This gives the compiler a way to optimize this however it wants. And then we say, okay, we clone some ascending end for everything. Shove it into the pool with move. Move statement here is important because we want this TX symbol, we want to have it gone. It must be copied into the thread and then no longer accessible to anything else. Here we have a very simple send the number 1. And this one, you know, unwrap, this is its bigger brother, except is really, really nice. Because if you have release mode code and it just says, hey, something panicked, then you look at it and like, sure. It panicked at option, line 400 something in standard library. Thank you. That doesn't help at all. But with except, you can have a message. And I usually start them with unable something, something, something. So I would have written unable to write to channel. In this case, I wrote it's there for sure. But, Usually I write stuff like that, right? Unable to da 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 da. Then when you add little details between these messages, even if they're from the same problem, if you search for the exact wording in the source code, you get it down to one line. That helps tremendously with debugging stuff. Other side note, I tried to use a debugger once or twice with Rust, and I stopped using them because usually the type system catches it, or I'm good enough with these expect statements, or just use print. Still works. Or in counters. Counters are also very handy. If you have stuff that's like statistically behaving, and then you have stuff in the range of millions, and you have some atomic U-size counters, and then you keep on for lower bounds or upper bounds, and then you look at the numbers and see, oh, it only runs 10,000 times. That's not possible. It should run 500,000 times. It gives you a feeling, or averages as well. Okay, so I guess up till here is everything clear. Drop, everybody knows drop. It's just an empty function, but why do we need to use it here?
So that the receiver can see the kind of end of
The channel.
Yeah.
Yes. You want to do
Yeah, same thing. Else the iterator would not end.
Correct. There used to be this recommendation that you should use take, but with take you can end the iterator after n elements. But this gives you a problem if your pool yields multiple things. Like I wrote the thumbnail generator once, and I wanted to have no redundant files because I was creating thousands of them. So I said, okay, only create the thumbnail if the image is bigger than the current size. So I had 3 sizes, I think 120, 300 something, and 1000 something pixels as the wide. That is at the longer end. So some pictures would yield 3 thumbnails, some just 1 or 2. And then this take would hang forever. Assert is also clear. Yeah, it's well commented. I don't have to talk too much. Okay. I wrote a load generator once to test out different CPU configurations and pinnings. If you look at modern big CPUs, so everything that has more than 16 CPUs has so-called NUMA units in them, and local and foreign memory, or near and far memory sometimes. I think AMD says near and far. This means when a thread runs on CPU 0 and requests some memory, CPU 0 might not have memory attached to it. But on NUMA node 3, CPU 27 might have memory attached to it. So CPU 0 has to communicate over the bus into another node to another CPU and tell it, hey, I want to have some memory over there. And then this has to travel back and forth. That's why if you ever have a big system and you're still doing hardware by yourself and you have weird memory latency issues, try to add more memory. But not too much because then it gets slow again. And AMD is way better with that than Intel because AMD has more memory things. Okay, anyhow, so what this code does is it gives every job, here is your input from the last one and here is your output to the next one, so you chain them together. And the idea of this test is to not put too much memory pressure on the whole system because it doesn't store all the intermediate results all the time because it keeps adding them up. And then it calculates pi. Let's step over here. Yeah. Stuff you can do. Questions or just like, meh. Should we go on or see some confused pieces? So from a hardware point of view, you can imagine this as you fill your CPU with one thread per physical unit, and then just let them run for, I think, 20 million iterations, and then after that, they will start to collect in like a wave over the whole silicon down to the last one, all the results, while at the same time on the top they start running again. So it gives the waves over the CPUs where the data just flows over the whole thing. Yeah. Less memory communication. Okay. There's a receipt. I have to be honest, I held a similar presentation in front of students once, and then they were like, but how can we actually do that? So we made this. Imagine you start with regular code. You have some vector with some pictures. Maybe they are not actually the pictures, but paths to the pictures, or just metadata that you have on them. And you process them by getting the length. And then, I don't know, maybe get something back from it, or you have the pictures are the receiving ends of channels, or something. And at some point, maybe return. Okay. So, oh yeah, and we want to push the information. Yeah, I remember now. So we receive for every picture and push it into this database. It's just a list of all the metadata of all the pictures. That works. It fails when some pictures don't get generated. Yeah, so we can use the iterator instead. Solve some problems. Then this is still pretty ugly. So let's get rid of that. We can say for each. Okay. Then at some point you might say, maybe I want to filter some paths. Maybe family pictures are not wanted in this collection or something like that. So can have map for that transition. And actually, we could have filter map before that. Yeah. And then here we are back at collect again. So we have this error early return thingy. We have that gone. Okay. And now we know that we get this result first if it ever occurred, and then we say, okay, collect into the thing, or expect unable to iterate through pictures. Gives us two messages, right? Gives us one message here that we can search for, and then when we know that, we can turn on, you know, this environment variable, Rust stack trace equals 1. Yeah, what's it called? Stack trace, yeah. Yeah, I think. Stack trace.
Maybe I'm wrong.
No, I'm bad with names, so
I could be wrong.
I'm probably wrong too. So enable that, then you get this message. Hooray! Okay, now parallelize with rayon. Did you see it? That's it. That's all of it. Import a library, add 4 characters. Done. That's the end. No, it's not quite yet. But just let that sink in for a moment. Uh-huh. We have been doing so much, and that solves.
What does it do?
So,
why do you actually just sort of if you do the other part like that, when you also how many CPUs you are by default?
maybe. So maybe you have all your CPUs maxed out. Maybe you decided, oh, I have multiple pools. Maybe I use only 4 for this task and 4 for another task. But it doesn't really matter because what you get here is a potentially infinite sequence. So it doesn't make much sense here to parallelize this because we only look if it had an error in the processing before. But if we did something else here, right, we could, I don't know, adjust some colors or calculate average pixel brightness or whatever. If we did that here, we could have a series streaming in, have them automatically distribute over our pool, and at the end still get our normal connection.
But not reduce.
Yeah, but with lots of type system working for you and giving that away too. Because you don't need to know, right? You don't care because it's an infinite sequence anyway. So yeah. If we were to collect the whole thing into a vector, then we could have the length of the thing and then could split it up into maybe chunks of 50 or whatever. Yeah. So, questions at the time? Ooh, on time. You see that? 45. So, more questions or I can have, yeah.
Is there any tools to observe the behavior of this parallel execution? How many threads it executes? What's the load of threads?
Mm-hmm.
Because now it looks like a black box. I drop some data, get some output somewhere, crash, and I start running again. Is there any tools to look inside? If rayon or in other system?
It's still hard, sadly. The best thing you can do is look with the system tools that you have, like the load average or CPU usage of top on Linux or HTOP or whatever you use. If you actually have performance problems at that level, you need to go to the vendor of the CPU and tell them to give you your debug tool. Like Intel has a good one, it's, Intel Perf or what's it called. Yeah. AMD has one. I don't think there is one for ARM, but yeah, it's not a problem so far. So, but the funny thing is when you have performance problems, usually the first thing you do is enable release mode, and then they're gone. So,
What mode, sorry?
Release mode. So the standard answer to any performance problem before parallelizing anything should be -- release enter. Right? It gives you speed up from 20 to 400 times depending on what you're doing. And that's just insane. You do nothing else. You can have the serial code as before. And sometimes serial code is still faster because of all the branch prediction and stuff like that. But when you want to know what's going on, counters is the thing I use. So I have a set of per task, then timers as well. What didn't work very well was having my custom timer. So I read about the system clock and how it might change, how NTP might slowly shift it over the day. But for my purposes, it never shifted so much that it affected me, and in the end, it was so horrible to get it right with loading the timestamp all the time that it just said, okay, forget it, make a system call. And fetch the time from the operating system. Yeah. There is an inspect filter, I don't know, it's a function that takes T and gives you T. You can insert that into the iterator and then maybe print it. Or if you don't want to print it to standard out, print it to a file. Or, yeah. It's a problem that hasn't been solved. More questions? I have 2 backup slides, so I can overdo it.
Can you go back to previous slides?
This one?
Yeah.
Mm-hmm.
So if connect to the results of vector and the arrow, will like early abort the whole iteration when the error happens. So what will it do to this parallel
Well,
task handling? Like, you stop all threads immediately, or it will wait for a while?
a year ago, this was undefined behavior.
Okay.
So I don't know if they decided on a behavior, but yeah. So the discussion back then was something like the overhead of communicating that this kind of job has to be aborted is so much higher that it's just not worth it in the general case. So when you want to have control over that, you have to have some abort signal. And then you're at the point where you're like, okay, do I still use rayon or do I use the ThreadPool? For my experiments, I was using the ThreadPool already, so I just added a symbol saying, yeah, like skip parts. So I had a function with like 4 parts in it, so I could skip some of them, or just abort the whole thing. Then you get the downside of checking every time, every thread has to. But atomic relaxed load is not that bad. I think it's 40 cycles on AMD. Yeah, it's 40 cycles on AMD, and it's something between 20 and 120 on Intel. Because Intel is magic. No, Intel is virtual. Actually, that's the reason. So when AMD released AMD 64, the architecture, Intel was like, oh shit, they had Itanium. Remember that one? Died off 10 years ago. Yeah, so they were like, oh, we have fast CPUs, but this instruction set, it's complicated. So they implemented it in software. They kept the design up to date. So every instruction you run into an Intel CPU, it gets analyzed, translated in some internal language, and then it's virtual. The instructions get routed on the CPU and the hyperthreading and all the fancy stuff they're doing. It's all happening with data routing on the chip. So, but there was this discussion once with these embedded people that said, oh, but I write assembler code because I want to know exactly which instructions the CPU executes in which order. Yeah, sure, you can do that, but the CPU doesn't care. It just takes the thing and looks at it and goes, oh. And when you're at that level trying to figure out what's happening, good luck.
I have a question. Would this be a pattern, like let's say that some of these computations are slow and others are fast? Would that be a pattern in which I can get the fastest computation of whatever I'm working? Because it seems to me that I have to wait until everything finishes before I can collect it, right?
Yes.
Is there some pattern with rayon or something that I can get the first computation and go as fast as possible and maybe tell the time, one of the results is great?
Well, it's a hard question to answer in the general case, but in this case, I did a workshop on that, on parallel programming in Rome, and then we had to learn something because we actually measured it, right? So we used the bench tools of Rust nightly, and then just iterated over it. It does some clever logic to figure out how many million times it has to run it. And then we realized the thumbnail generation process inside the image library already uses rayon. So they parallelize the image resizing already internally. So that task is happening while your task of analyzing the image for metadata or artifacts or something like that is also running concurrently on that pool. So some tasks fall out of the pool and some others are queued back and forth. So yes, that works. But how does that work with like RPC, I guess, is your question. Right?
Also, you mentioned a little bit of work stealing, so I'm wondering if this is going in the same direction or if rayon is completely separated.
There is one global pool per application for rayon. It's also the hidden global default pool. So yes, if you have an event loop dispatching, I don't know, HTTP requests into the pool, there will be only one pool executing all of the queries. Might be a problem because your new short request might stand in queue behind 4 or 5 longer ones. But after if you have like most of your jobs are short, and they come in asynchronously, and some of them are long, and the long ones are not too close together, then this could work. Yeah.
You could also use a channel to like send the words back to the main file. If there are use differences in that.
Yeah, but then you can't use rayon anymore.
Okay.
Then you have to use ThreadPool or futures.
Sure. Yeah.
What's not possible in current Rust is yield. So when you have a long job and then you know it's a long job, when you have Java, then you just yield, right? And then it reschedules another job. So that doesn't work. What you could do is implement your job in multiple steps, like in multiple futures. And then when it spawns the new future, it will implicitly yield sometimes, and therefore free the pool again. And yeah, and with pools and channels, you would have to resubmit your next step onto yourself. It's a bit ugly in the code, but it's doable. You have to do it yourself. Okay. Generally speaking, there's my list. No, we went too far. There's the list. Here you see this. Yeah, this list. The job queue thingies are, yeah, that's the different job queue and work stealing. And with futures, we might have less of this problem. Especially when you have I/O bound stuff with the futures that will be coming this year. This will automatically insert the gaps that you need for the fast response time. Yeah. Cool. More questions? Okay. So let's go. Thank you. One giveaway for the break. You can either do an elaborate scheme or I will just throw it over my back. Which would you prefer?
Throw it.
Throw it?
Yes.
Okay. So I will close my eyes and then you have to tell me if I'm looking more or less at the wall and then I will throw it, okay?
Yes.
So.
Now?
Okay.
No. No. Yes. No.
No.
Yes.
Yes.
Yes. Okay. All right.
Thank you very much. That was interesting. Let's take a break of 10 minutes, 10, 15 minutes, and then.